Swayam Prabha. Digital India. Educated India.
Hello everyone. Today we will discuss a very important topic in nano Mosfet electrostatics, which is the 2D electrostatics of Mosfets. And if you recall, what we have been discussing so far is actually 1D electrostatics, which means that we have only considered the Poisson equation in y direction, which is the direction normal to the channel, which is from the gate through the channel to the substrate or to the body, this direction only. And there are valid reasons to do that, because in conventional MOSFETs, the thing is that the electric field in this direction and especially in this region is extremely strong as compared to the electric field in this direction. Or in other words, what happens is that this quantity, the second derivative of the potential which appears in the Poisson equation, that is, so this del 2 psi by del y square is large as compared to del 2 psi by del x square in the case of long channel or in case of conventional MOSFETs. And that is why we can just do proper electrostatic treatment of the MOSFET just using the electrostatics in y direction, because if we consider the electrostatics both in x and y direction, in that case the Poisson equation will look something like this: del 2 psi by del y square, it should be equal to rho by epsilon s. Okay. But in most of the conventional MOSFETs, this quantity is almost 0, or this is extremely small as compared to this one. And so that is why we can just solve this Poisson equation and do our electrostatics, which is the conventional electrostatics in MOSFETs. So just to quickly review that, what we have seen is that that in order to understand this 1D electrostatic picture, we sort of tilt the MOSFET in this direction so that this y direction becomes the horizontal direction, and the bands look like this in various regimes of MOSFET operations. This is the accumulation regime when a negative gate voltage is applied on a N MOSFET, which means that this negative gate voltage will attract a lot of holes at the interface of oxide and semiconductor, and it will lead to the accumulation of holes. This is the flat band situation, and this is the depletion or inversion region when a positive gate voltage is applied. So this picture, this band diagram picture in y direction when the MOSFET is tilted, this gives a very good intuitive understanding of the electrostatics of the MOSFET and MOS capacitor. Second is, after so we have already gone through this, and after this we saw that the semiconductor charge Qs and the surface potential, the semiconductor surface potential, which is the electrostatic potential right at the interface of the oxide and the semiconductor at this point, which is just the beginning point of the semiconductor. This follows this kind of relationship, and as we can see that for low psi s values, the MOSFET is operating in depletion regime, and in the depletion regime the charge is directly proportional to the square root of psi s. But for a large positive value, the MOSFET operates in inversion regime, and in inversion regime the charge is mainly due to the mobile electrons, and that has exponential dependence. So this is the depletion charge, and the inversion charge has the exponential dependence on psi s. The total semiconductor charge, this Qs, is actually the sum of Qd plus Qn, which is the depletion charge plus the charge due to inversion or the charge due to mobile carriers. In the accumulation regime, there is no depletion, and the only charge that is there is because of the accumulation of majority carriers, and that has exponential dependence. So this is an important relationship of the semiconductor charge as a function of semiconductor surface potential, because this gives us a lot of idea of how things are going on at various gate voltages. Then we also saw the relationship between psi s and Vg, which is the dependence of psi s on the externally applied gate voltage. Vg is the voltage that we apply on the device, and psi s is the voltage that appears on the interface. Finally, most of the electrostatics is governed by this psi s, but this psi s is controlled by the Vg voltage. So we would also like to understand the relationship between psi s and Vg, and this is how it looks like. And as you can see from this picture, below threshold voltage, the psi s voltage is approximately equal to the applied gate voltage. So the psi s curve follows the Vg line, but as soon as the gate voltage approaches the threshold voltage and it is more than the threshold voltage, in that case the psi s does not increase much, because the semiconductor charge, which is the inversion charge, increases exponentially, and this exponential increase in semiconductor charge actually increase the voltage drop across oxide, because the voltage drop across oxide is minus Qs divided by Cox. So if this Qs is more, then delta Vox will be a large number. So, so this is the relationship between psi s and Vg. So that's how we can understand the relationship between Qs and Vg, if we sort of couple these two, both of these plots. Finally, there is so we have seen that the depletion charge is directly related to the surface potential via this relationship, and we would also like to know how the mobile charge is related to the gate voltage. So this is I would say a qualitative picture of the relationship between Qn, which is the mobile charge in the MOSFET, which is the charge due to the inversion layer, due to the electrons in the inversion layer. And as we can see from this plot, that in the subthreshold regime, which is the case when Vg is less than Vt, in that case Qn is extremely small number, and it's almost equal to 0, well below the threshold voltage it is almost equal to 0. It starts increasing exponentially as the gate voltage approaches the threshold voltage, and then it increases abruptly. Okay. Finally, what we see here is that this Qn can be written in terms of the gate capacitance above the threshold voltage, and it follows this particular relationship, because the gate capacitance also involves the semiconductor and oxide capacitance. So after a certain value of Vg, once the Vg is greater than Vt, in that case Vg is well above Vt, in that case this gate capacitance is almost constituted by the oxide capacitance, and that is why we see this linear kind of relationship. After that, we saw how to derive the threshold voltage for the MOSFET, and the threshold voltage looks like this. The threshold voltage is equal to the flat band voltage, which is the voltage that we need to apply in order to align the, or in order to flatten the bands in the semiconductor when the Fermi levels of the semiconductor and the gate are not aligned. So, in many cases what happens is, without any externally applied voltage, the Fermi level of the gate and the Fermi level of the semiconductor are not aligned, and that is why there is a bend bending at 0 bias, and in order to neutralize that bend bending we need to apply the flat band voltage. So, by considering the flat band voltage and the depletion charge, this is the formula for the threshold voltage, and as we can see, the threshold voltage is the voltage when the semiconductor potential psi s is equal to 2 psi b, which means that the semiconductor at the interface is as n type as the semiconductor is p type in the bulk. So, after that we saw the notion of gate capacitance, and which is the capacitance as seen from the gate terminal, and as we know that if we look from the gate terminal we would come across the oxide capacitance, which is a dielectric capacitance and is a constant capacitor, constant value capacitor. The capacitance will be constant for the oxide, and then beyond the oxide we have the semiconductor, which is a voltage dependent capacitor, because the semiconductor capacitance changes as the gate voltage or the surface voltage psi s is changed. Because when the psi s value is positive, in that case first the depletion region appears where the depletion capacitance comes into picture, and then the inversion layer comes up where the inversion by considering the inversion capacitance in inversion layer as well, we realize that the semiconductor becomes like a metallic plate, and in that case the capacitance changes as compared to the depletion capacitance. So, the semiconductor is a voltage dependent capacitor in a way, and in that, so that is why we have we see here that this gate capacitance is a series combination of oxide capacitance and a voltage dependent semiconductor capacitance, and it has a frequency dependent, which we discussed last time. At low frequencies in a MOS capacitor, this would be the behavior of C as a function of Vg. At high frequency the capacitance will be low, because in a MOS capacitor the inversion layer cannot respond to the applied gate voltage at high frequencies. However, if we talk about the capacitance of a MOSFET, in that case the capacitance of a MOSFET will look like the low frequency plot, because in MOSFET the inversion layer, the minority carriers, in order to make inversion layer, they can come from the contacts, and the mobile charge carrier density inside the semiconductor is given by these relationships which come from the carrier statistics in semiconductors. So, this is all what we have seen so far in the discussion of the conventional electrostatics of MOSFETs. Now, and this is what we saw last time, that the relationship between psi s and Vg can also be written down in terms of the capacitances, in terms of the gate oxide capacitance and the semiconductor capacitance. And if we sort of model this MOSFET as a series of two capacitors, in that case we realize that Vg is the voltage at the top of these two capacitors, psi s is the voltage in between, actually in between Cox and Cs. So, then according to the voltage division rule across capacitors, psi s can be written as Vg times Cox divided by Cox plus Cd, which means that we can write it down as Vg divided by M, where M is Cox plus Cd divided by Cox, which is 1 plus Cd by Cox. So, this n, as you can see, is a number which would be greater than 1, because it is 1 plus Cd by Cox, and from this relationship psi s equals Vg by M, we see that if M is larger than 1, M is a large number, in that case psi s would be small as compared to Vg. and if m is closer to 1, in that case psi s will be almost equal to Vg. So, this m, which is known as the body coefficient of the MOSFET, it actually governs how much of the gate voltage will drop across the semiconductor, because the voltage that drops across the semiconductor is psi s. So, if this m approaches 1, in that case psi s will almost be equal to Vg. And what does that mean? It means that if m is almost equal to 1, in that case most of the gate voltage is dropped across the semiconductor, which means that the external voltage that we are applying on the gate is totally used to deplete the MOSFET or invert the MOSFET, or to create the inversion layer in the MOSFET. So, ideally we would like m to be as close to 1 as possible always. So, we always try to make sure that m is as close to 1 as possible. Okay. So, that is a design constraint that we keep in mind, that while designing a MOSFET, generally the device designers try to make sure that m is not far away from 1. And in order to bring m closer to 1, what needs to be done is that this second factor CD by Cox, this needs to go to 0 actually. So, we need to make CD by Cox as small as possible. So, how do we do that? We can do that by two ways. One is by having a small CD, by making CD as small as possible, or by having a large Cox, which means we would like to have Cox as large as possible and CD as low as possible. So, in order to have CD as low as possible, we need to have a lightly doped semiconductor, because as you recall, CD is directly proportional to the doping of the semiconductor. So, if the doping is less, in that case CD is extremely smaller than Cox, and in that case m approaches 1. The second way is if you, by taking a very thin oxide. So, if you recall the formula of Cox, Cox is epsilon ox divided by Tox. So, this is the Cox per unit area, the oxide capacitance per unit area, and if T is extremely small, in that case Cox becomes larger, and in that case CD by Cox becomes smaller. So, by making a very thin oxide, we could make sure that Cox is extremely large as compared to the depletion capacitance, and that way we can bring m closer to 1. But there is a trade off in making a very thin oxide, because as soon as the oxide thickness goes below 2 angstroms, in that case what happens is that there is a tunneling of carriers from gate to channel. So, there the tunneling current from the gate to the channel starts becoming prominent, and we would always like to avoid that. So, we cannot always make a very thin oxide, or in fact making oxide thinner than 2 angstroms can severely impact the functioning of the MOSFET, because in that case the tunneling current would increase and this drain current will be disrupted. So, the other way to increase Cox is we would like to have larger epsilon ox. So, the dielectric constant of the oxide, if it is larger, in that case epsilon ox will be large, and we can ensure that m is closer to 1. So, which means that we need to use high K dielectrics. So, this high K dielectrics is a new area, is entirely because generally in MOSFETs silicon dioxide is the oxide which is used as a gate oxide, and the reason for using silicon dioxide is the ease of fabrication, because we can just oxidize a very thin silicon layer to make silicon dioxide, and in that case we do not need to worry about the matching of the oxide and the silicon, and even the interface charges can also be controlled to a large extent But if we want to use high K dielectrics, which means the oxides which have high epsilon ox, in that case we would need to put another kind of oxide on top of silicon, and in that case we need to keep many things in mind. One factor that we need to keep in mind is that the lattice of the silicon and the oxide should match, the bands should also match. So those kind of constraints when we need to keep in mind. But generally the high K dielectrics that are used in the MOSFET fabrication are hafnium dioxide, hafnium silicate, zirconium dioxide and zirconium silicate, because these dielectrics, they are it seems that they have high dielectric constant, as well as they can be fabricated in a much better way as compared to the other oxides. Okay, so we will again come back to this point of high K dielectrics. Apart from having a better body coefficient, we again, these high K dielectrics are also useful to make smaller or miniaturized devices, because as we miniaturize the MOSFET, in that case the oxide thickness also needs to be made smaller in order to have a better current. And for that, and as we just discussed, that we cannot make oxide arbitrarily thin, because that would lead to increase in the tunneling current, tunneling from the gate to the semiconductor. So the other way is, in order to have high oxide capacitance, we use the high K materials, high K dielectric materials in smaller MOSFETs. Okay. So we will come back to this point again, but this essentially concludes our discussion of the conventional electrostatics of the MOSFET, and a large part of this is also applicable to the nano MOSFETs. Okay. Now we will see the 2D electrostatics, actually how the electrostatics change in small MOSFETs. And again, just to quickly review, the electrostatics, in electrostatics we are mainly concerned about the charge in the channel, which depends on both VGS and VDS. And this is the picture of a MOSFET. In this picture, as you can see, there is a source, there is a drain, and there is a gate terminal, and there is a barrier in the channel between the source and the drain, and this barrier is controlled by the gate terminal and the drain terminal. So what does the gate terminal do? The gate terminal essentially lowers the barrier. So the barrier height depends on the gate terminal. And what does the drain terminal do? Drain terminal essentially brings down the Fermi level of the drain side, or the drain voltage brings down the Fermi level of the drain side, which essentially allows a net flow of electrons from the source to the drain. So that way we have a properly well defined tasks or well defined functions of the gate and the drain terminals. By using the gate voltage, we can control the barrier height, and by using the drain voltage we can control the symmetry of the barrier to allow the electron flow from the source to the drain. So this is the ideal scenario in which ideally the barrier height should only depend on the gate voltage and not on the drain voltage, because if the barrier height depends on the drain voltage, then it creates a kind of non-uniformity across various devices, because various MOSFETs might be operating at different drain voltages. Some might be at 0 drain voltage, some might be at 1 drain voltage or high drain voltage. So in that case there might be a non-uniformity between various MOSFETs. So ideally this barrier height should only be dependent on the gate voltage, and that's again I would say is one of the things that the device designers keep in mind while designing a good MOSFET, that this barrier height should not depend on the drain voltage. And we have seen it earlier as well, that Especially in smaller MOSFETs, what happens is, so this is here we have two figures. The top figure actually is the ideal case in which this barrier in the channel is shown for two drain voltages. This is the low VDS and this is high VDS. And this barrier height or the peak, this top of the barrier, the peak on the source side, it does not change with VDS. So, this peak is the same for both high VDS and low VDS. So, this is what we try to ensure while designing a MOSFET. So, only the gate terminal controls the barrier height, okay. But generally in smaller MOSFETs, in small channel MOSFETs, what happens is at high VDS, even the barrier height is actually lowered by some value, and this is known as the drain induced barrier lowering, which we have already seen, and this is best characterized by the subthreshold plot, which is the plot of log ID as a function of VGS for various VDS voltages. So, this is the plot for VDS equals to 0.05 volts, a small VDS, and this is the plot for high VDS, 1 volts. And as you can see that as the VDS is becoming higher, this ID versus VG plot is shifting to the left side, which means that that the threshold voltage is now lowering. So, this is this results in the change in the threshold voltage, and that is why the threshold voltage most of the times is written as Vt is equal to Vt naught minus delta VDS, where delta is the DIBL factor. Delta, so Vt naught is the threshold voltage in ideal case and delta is the DIBL parameter. So, it shows that Vt also changes with VDS, which is what we want to avoid. Also, more generally in small channel devices, there is this kind of phenomena are summed up in a plot of Vt versus L, threshold voltage versus length. So, what it shows is that the threshold voltage is ideally independent of the length for most of the lengths of the MOSFETs, but as soon as the MOSFET length, the device length starts getting smaller than a certain value, then there is a reduction in the threshold voltage. So, the threshold voltage Vt becomes dependent on the channel length, and this is known as the threshold voltage roll off. One of the reasons of the roll off is DIBL. There might be other reasons as well, because as soon as the threshold, as soon as we make smaller devices, the depletion regions. So, let me quickly demonstrate it here. This is a typical MOSFET. We have a source, we have a drain, we have an oxide, we have the gate terminal. If this channel length is shrinking, in that case what happens is the source and the drain are coming closer to each other, and since the source is N type or N plus type, the semiconductor is P type, the drain is also N plus type. So, there is a depletion region, because this is a PN junction and there would be a depletion region around the source and the drain junctions. So, what happens is that in smaller devices, these depletion regions can become significant part of the channel. So, which means that now there is a smaller charge that or a smaller voltage that is needed to deplete the channel, because a large part of the channel is already depleted because of these PN junctions, the PN junctions between the source and the device, and the drain and the body, source and the body. So, only this part of the channel needs to be depleted by the gate voltage. So, that is why we need smaller gate voltage in order to totally deplete the channel region, and which means that we need smaller voltage to make an inversion layer, and which means that the Vt becomes smaller. So, generally this is the phenomena, this Vt roll off, the threshold voltage roll off is observed in smaller MOSFETs, and this is a typical small channel effects. This is a consequence of the small channel effects. DIBL is one of them. So, in order to properly characterize and understand all these things, we need to deal with the 2D electrostatics of the MOSFET. So, by understanding the 2D electrostatics, we would be able to understand these phenomena, and we would be hopefully able to solve some of these problems as well. So, that is what we will do now. We will try to see how the 2D Poisson equation looks like in the MOSFET. So, this is the general picture of our MOSFET. The channel direction is the x direction, and the normal to the channel, which is from the gate to the body, is the y direction. In this direction, the VGS voltage is applied. In x direction, we generally apply a VDS voltage. Okay. In smaller devices, we have already seen that the electric field both along the channel and perpendicular to the channel are important, and that is why we need to consider the 2D electrostatics or 2D Poisson equation, which is we need to write the Poisson equation in both x and by considering the charge distribution both in x and y direction due to the electric field in x and y direction. So, the 2D Poisson equation looks like this. So, the general Poisson equation is del dot D is rho. Rho is the special charge distribution, D is the displacement electric field vector, and in 2D in both x and y directions, dxy is epsilon s, which is the dielectric constant of the semiconductor times the electric field as a function of x and y. So, now we are considering both electric field in both directions, both in along the channel x direction and perpendicular to the channel y direction. So, that means that this Poisson equation del dot D can be written as del dot E rho by epsilon s, and in 2D the electric field is the gradient of the 2D potential in the semiconductor. So, now this semiconductor potential psi, this also becomes a function of two variables, both x and y. So, so the 2D Poisson equation ultimately will look like this. If we substitute E is equal to minus del psi xy in this equation, so this equation will be del 2 psi xy minus rho xy divided by epsilon s. So, this left hand side is essentially del 2 psi by del x square plus del 2 psi by del y square is equal to minus rho, which is the charge density in the semiconductor divided by the dielectric constant of the semiconductor. So, this is the 2D Poisson equation in the channel region of the semiconductor. And if we quickly recall the 1D Poisson equation, the 1D Poisson equation looks like this. So, this is the 2D Poisson equation. The 1D Poisson equation looks like this, and generally the most prominent impact of the 2D electrostatics or most prominent impact of the small channel effects happens in the subthreshold regime, which is just at the beginning of the inversion. Just before the inversion or around the inversion regime, That is where we notice the effect of the 2D electrostatics, as is also clear from here. So, we see that the voltage, the threshold voltage rolls off, which means that the voltage at which the channel is getting formed, the channel is getting inverted, is getting smaller, and the IV curve, the transconductance curve ID versus VGS, is getting shifted to the left side, and this is visible, or this is prominently important around the threshold voltage. So, just at the beginning of the inversion, what is the charge in the channel? Just at the beginning of the inversion, we generally assume that the charge due to the electrons, the mobile charge, is negligible as compared to the depletion charge, which is also true. That is what we have also seen earlier. So, this rho xy just at the beginning of inversion can be written as the charge due to the depletion, just due to the depletion. In general, this rho is actually Q, this is the charge due to holes minus the charge due to electrons plus the charge due to ionized dopants minus the charge due to ionized acceptors. So, generally this is the space charge density in the semiconductor, but just at the beginning of the inversion, this is 0, this is 0, and we are assuming the p-type semiconductor. In that case, this is also 0. So, what is left is only this, and we assume the total ionization of the acceptor atoms, which means that this rho xy is equal to minus q na, because this q na minus is equal to q na. So, the right hand side becomes del 2 psi by del x square plus del 2 psi by del y square is equal to q na by epsilon s. And we will also do a parallel analysis of the 1D electrostatics just to see the difference that arises due to the 2D electrostatics. So, similarly in the 1D electrostatics, just at the onset of the inversion, this Poisson equation will look like this: del 2 psi by del y square is equal to q na divided by epsilon s. So, this is the 1D electrostatics or 1D Poisson equation. And this is the 2D Poisson equation. Now, as you can see that the right hand side is the same in both cases, there is a change in the left hand side. In 2D Poisson equation, in addition to del 2 psi by del y square, we also need to consider del 2 psi by del x square. So, what that amounts to is that we can take this term to the right side, del 2 psi by del x square, and the left hand side of this equation is exactly same as the left hand side of the 1D Poisson equation. So, this 1D analysis is the analysis that we have already done so far in our discussion of electrostatics. And if we consider the 2D electrostatics because of the small channel, in that case this Poisson equation can be written as del 2 psi by del y square is equal to q na by epsilon s minus del 2 psi by del x square. So, there is a small difference between this 1D Poisson treatment and this 2D Poisson equation. Okay. So, so ultimately this is the equation that we have in 2D Poisson equation. And so, now what is this term? Let us try to sort of make sense of this term, del 2 psi by del x square. Let us draw a picture of the Mosfet. This is how the Mosfet looks like, and since we are considering the 2D electrostatics, in that case we are assuming that we have applied a voltage on the drain terminal in addition to a voltage on the gate terminal. The source is assumed to be grounded, the body is also assumed to be grounded. Psi is the electrostatic potential in the semiconductor. The first derivative of the psi, del psi by del x, and negative of that is the electric field, and del 2 psi by del x square is the curvature of the potential profile in x direction, So we need to see what is the curvature of the potential profile in x direction in order to understand this term. And please also remember that the psi electrostatic potential is also closely related to the conduction band edges, and it has a negative relationship, because the conduction band edge or the valence band edge or the bands in the semiconductor, they essentially represent the potential energy of the electrons, and the potential energy is equal to minus q times the electrostatic potential. So this EC and psi has a negative relationship. Okay. So in order to understand the curvature of the potential profile, we will see the curvature of the bands in the semiconductor. So and we are familiar with the bands because the bands we have seen many times now. So this is how the barrier actually looks like in the semiconductor when we apply a certain drain voltage. So this is the top of the barrier, this is where actually we think that the source is located. So this is also known as the virtual source point of the device, because this is the point where the gradient of the band is 0, which means that the electric field is 0. So the velocity at this point is extremely important. We have already seen that, that is known as the unidirectional thermal velocity, also known as the injection velocity. So after this point, what we see is that the curvature here is, the curvature of this plot is 0 here, but the curvature becomes negative here. If you see, the curvature at these points are negative, and here again it is 0. So along the channel, the curvature is either 0 or negative, and this is the curvature of the conduction band edge, because in order to understand the barrier, generally we plot the conduction band edge in the device from the source to the drain side. So it means that the curvature of the conduction band is negative. If you are not familiar with the notion of the curvature, generally what happens is, if there is a plot like this, the curvature is positive, because if we do the second derivative, it turns out to be a positive value, and in this kind of relationship, the curvature at these points is negative. In the channel, actually the things are assumed to be starting, or the electron injection is assumed to be starting from this point, and this point onwards the curvature is negative for this conduction band edge. So the curvature of EC, which means del 2 EC by del x square, is a negative number, which means del 2 psi by del x square will be a positive number, because they are negatively related to each other. So that's the key point here, that in a MOSFET, del 2 psi by del x square is a positive quantity, and the 2D Poisson equation, which looks like this. Now if we compare this to the 1D Poisson equation, del 2 psi by del y square, which is q n a divided by epsilon s, in addition to, so in the 2D electrostatics, in addition to this factor of q n a by epsilon s, we also have a positive quantity del 2 psi by del x square. So which means that now we or what we can do is we can write this down as QNA effective divided by epsilon s, where QNA effective by epsilon s is equal to QNA by epsilon s, this value, minus del 2 psi by del x square. And what we have just seen is that this is a positive quantity. So, this Na effective is actually less than Na. So, this Na effective is the effective doping of the semiconductor when we consider the 2D electrostatics. Okay. So, what it means is, what we can say is, if this term is dominant, del 2 psi by del x square, in that case we can write down the 2D Poisson equation just like a 1D Poisson equation, and hence all the things that we derived for 1D Poisson equation can be used here as well. But now instead of Na, we need to consider Na effective, which is a smaller number than Na. So, what it means is that the 2D electrostatics effectively reduces the doping of the semiconductor. So, what it means is that now in all the expressions that we have seen for semiconductor, for the threshold voltage, for the depletion width, we need to replace Na by Na effective. So, that is the impact of the 2D electrostatics. Okay. And now this Na effective is smaller than Na. So, I will give you this small sort of homework assignment to look how various parameters will change while considering the 2D electrostatics. So, how the depletion width will change, how the depletion charge will change, how the threshold voltage will change while we consider the 2D electrostatics, or this term del 2 psi by del x square is significant. When this is significant, how does all those things change? Because what we have seen is that the 2D Poisson equation can be converted to just like, or converted to a 1D Poisson equation like this. What we just need to do is we need to replace Na by Na effective in all the expressions that we derived for the 1D Poisson equation. So, just please go back and look into how things change, and that is what we will discuss in the coming class. So, thank you for attending this lecture. See you in the next class.